Okay, everything that we've looked at in previous chapters has been kinematics, which is the description of motion. And now we're going to start looking at the causes of this motion, causes of the change in motion. And this branch of mechanics is called dynamics. So dynamics look at the causes of changes in motion. And what causes a change in motion is a force. Okay, so we have here a force. And we usually denote this as just a capital F for a general force. It is a vector quantity, so it requires both a magnitude as well as a direction to fully describe it. The SI units are the metric units, are newtons, which we denote with a capital N, and in the English units, or the US units I should say, US customary, the units are pounds. So, and the abbreviation for pounds are LB. So force, vector quantity, we'll typically use newtons as its units. We'll stick with the metric system mostly. So what is a force? A force is basically, a force is a push or a pull. So we could have, if your hand is pushing on this, then we have a force going off to the right here. Or I could attach a string and I could pull it off to the right. So it's some sort of a push or a pull. We could also have gravity pulls down on something, and so this is a force as well. And we can take forces and we can break them up into two different categories. We have contact forces and we have field forces. So contact forces and field forces. Now, contact forces, as the name suggests, are forces which make physical contact. So for example, this hand pushing over here, this was a contact force. Also, the string was attached to this block, and the string was in contact with the block, and so this was a contact force as well. So other examples of some contact forces we have, like a hand pulling on a spring here. The hand pulling on the spring is a contact force, and also the spring pulling on the wall over here is a contact force. A lady pulling the cart. Obviously the handle's in contact with the cart, so this is a contact force. Somebody kicking a football, the foot is in contact with the football, and so this is a contact force. Field forces don't make a physical contact. They act over a distance, and so gravity is one of them. Gravity is a field force. It acts over a distance. Gravity doesn't need to touch something in order to act on it, and so gravity is an example of a field force. And this is actually, we'll see this later on, that gravity depends on both of the masses. So this is the gravitational force here in D. Also, we have other field forces, like in F here, we have a magnetic force. So magnets act over a distance. The magnets don't actually have to touch for the forces to interact there. So magnetic forces are field forces. Also, electrical charges, they act over a distance as well. And so electrical charges are also a field force as well. It's like nuclear charges. So we have contact forces and field forces. The only field force that we will deal with in mechanics is the gravitational force. So just this one here, just gravity. The electrical forces and magnetic forces are covered in electromagnetism, which is Physics 152 next semester. So considering these contact forces, we can break them up into a couple other types of contact forces. For one, if we look in this first figure here, if we have a box sitting on a surface, then the surface exerts a force onto the box, right? The box also exerts one onto the surface, but let's focus on the force that the box exerts, or the floor exerts onto the box, and the direction of this would be perpendicular to the surface itself. So if I drew this down, then this would be perpendicular right here. So we called this the normal force. Normal meaning perpendicular. So this is our normal force. And we abbreviate this with a lowercase n. And it's a vector as well. So if we have a slanted surface, then the normal force is still perpendicular to that slanted surface. So it's not like that. And we have this. So a normal force is the force exerted by the surface on the object, and it is normal to the surface, perpendicular to the surface. In addition to the normal force here, we also have a frictional force, and the frictional force is always parallel to the surface. So this one is the frictional force. So this is friction, and we denote friction with a lowercase f. Generally, uppercase f is reserved for just a general force, lowercase f is a frictional force. And the important thing about friction is that it always goes in the opposite direction of motion. So it always opposes motion. So we see here this box is moving off to the right, and so the frictional force is to the left. So the frictional force is parallel to the surface, and it opposes motion. And we'll investigate this in more detail later, but if we have this direction of the motion or the attempted motion, if we just push on it but we're unsuccessful in actually moving it, there would be attempted motion. If the direction of our attempted motion is to the right, then the friction would act to the left. And this all comes from, it's the interaction, if we zoom in here, it's the interaction between the roughness of these surfaces, but we'll investigate that in more detail later. So it's parallel to the surface and opposite the direction of the motion. We also have tension. Tension is another contact force. So if we attach a string here and pull on it, then the tension pulls out this way. So tension is always a pulling force. It's exerted on an object by like a rope or a cable or something, and if you try to push with a rope or a cable, the rope or cable kind of collapses. It doesn't actually push anything. So we can only pull with a tension, and this could be any angle that we want, same as a regular force there. So this is tension, which I will denote oftentimes as just Ft, since we have another thing we'll call T later. So the tension force. Another quick note on the tension. In this class, we'll assume, unless it's otherwise stated, that we have an entirely massless rope. So the mass of the rope itself won't be any additional weight or force. So if we have a massless rope, like we have both of these cases, here and here, we have a massless cable or massless rope. In the first figure, we have some weight over here with some force going down like that, and then we have some weight here with some little force going down like that. And then these are connected by this string. Okay, so they're connected by a string here. It goes all the way up around like this. And the tension in this string is always pulling. So if it pulls on the leg up like this, and it also pulls away. If I were just to look at the forces on this little point here, it pulls away like that, pulls away like that. And its magnitude, you'll notice here, it's always T. This tension stays the same everywhere throughout the rope, as long as it's a massless rope and we don't have any other weights along the way in the middle of the rope. If I had put another weight right here, then the tension on this side would be different on this side. And this is kind of what we have actually in the second figure here. We have a rope along like this, and there's a lady hanging off of this rope right in the middle here. And so this rope itself is massless, so we can say the tension everywhere in here is all tension 1. Anywhere in here, the tension would be tension 1. But then because there's this other mass right here, on the other side of that mass, we're going to have a different tension, T2, but it'll be the same everywhere throughout here. So we'd have two different tensions in this case because of this mass, this weight in the middle here. And lastly, weight. Weight is simply, we'll get into more detail on this later as well. Weight is the pull of gravity on an object. It is the gravitational attraction force. So it's just anything with a mass on Earth or near the Earth has a weight, and the direction of the weight is towards the Earth, right, or towards the center of the Earth. So that's weight is the pull of gravity on an object.